Welcome back to the deep dive. Today, we are tackling something that, it feels like the simplest thing in the world, but it turns out it's a physiological miracle. We are talking about looking.
It's the ultimate illusion of simplicity, isn't it? You wake up, you open your eyes, and the world is it's just there.
Instantaneous.
Completely. It feels effortless. You see your coffee cup on the table, you reach out, you grab it. You don't think for a second about the machinery behind that action.
Exactly. It's like the perfect user interface.
Yeah,
It's so good, so seamless. We totally forget there's a massive operating system running underneath.
a huge one.
But the stack of research we have in front of us today, we've got textbook chapters on sensation and perception, lecture slides, notes. It all paints a completely different picture. This isn't just opening the shutters on a window.
Not at all. It's a massive, unbelievably high-speed chain reaction. You're talking about physics, chemistry, biology, electricity, and then some of the most heavy-duty data processing imaginable, all happening in a fraction of a second.
It's the most complex biological machine we have.
It really is. And our mission for this deep dive is to try and decode that. We're going to unpack what scientists call the perceptual process loop.
Okay, so what does that mean?
It means we're going to follow the signal. We're going to start with an object out there in the environment, a tree, a car, a face, and we're going to trace its journey until it becomes, well, electricity inside your brain.
And we have a massive checklist for this. Looking at our notes, we have 82 specific touch points to hit.
82.
Mhm.
And they cover everything. The hardware, which is the eye itself, the software, which is how the brain processes the signal, and even the philosophy of how we know what we know. It's a huge topic.
A lot to get through. So let's start at the very beginning with the absolute basics. We have these two terms that I think most people use interchangeably: sensation and perception.
Right. And in casual conversation, that's fine. But for our purposes, they are not synonyms. Making that distinction is like step one.
So what's the difference?
Think of sensation as the raw data entry. It's the biological hardware reacting to the physical world. A photon of light hits a receptor in your eye. That's a sensation.
It's just the detection.
It's a detection. A sound wave vibrates a tiny hair cell in your ear. A sugar molecule lands on a taste bud. It's purely physiological. It's the hardware reporting that something happened.
Okay, so sensation is the raw signal. What's perception then?
Perception is the next step. It's the conscious sensory experience. It's your brain taking all that raw data, organizing it, interpreting it based on your past experiences, and finally giving it meaning.
So sensation is a specific pattern of light just hit my retina.
Exactly. And perception is, that's my grandmother, and she looks happy to see me. You see the difference. One is data, the other is meaning.
That's a huge leap. And looking through the source material, there's this recurring question that comes up. Why even study this? It's obviously fascinating, but why is there a whole scientific field dedicated to perception?
Well, the practical reasons are pretty clear. The medical applications are enormous. If you want to fix vision, if you want to cure blindness or deal with conditions like macular degeneration or retinitis pigmentosa, which we will absolutely get into,
Right.
you have to know the mechanics. You have to understand how the machine works before you can fix it.
That makes sense.
But there's a deeper reason too, a philosophical one. We only know that the world exists because we perceive it. Everything you know, everything, history, science, the faces of your loved ones, it all had to pass through this perceptual filter first.
It's our only window to reality.
It is. So understanding perception is really about understanding the fundamental machinery of how we know anything at all. It's the interface between us and everything else.
Okay, that's a big idea to start with. So let's try to unpack that process. The notes talk about this battle almost between two different ways of processing information: bottom-up processing and top-down processing.
This is one of my favorite concepts. It explains so much about how we navigate the world and why optical illusions work.
So let's start with bottom-up. What is that?
Bottom-up processing is purely data-driven. Think of it as building a perception from scratch. You're looking at the raw inputs, the pixels, the lines, the curves, the colors, and you're assembling them in your brain to figure out what you're looking at.
Like looking at a weird piece of abstract art for the first time.
That's a perfect example. You don't have any prior knowledge of what it's supposed to be, so you're just analyzing the components. The red splotch here, the sharp line there. You're building from the bottom up.
Okay, so then top-down must be the opposite.
Exactly. Top-down processing is knowledge-driven. It's when you use your high-level expectations, your memories, your context to interpret ambiguous data. Your brain makes an educated guess.
Can you give an example?
Sure. Imagine you see a blurry, blobby shape in a kitchen. Your brain, using the context of kitchen, immediately guesses toaster or blender. But if you saw that exact same blurry shape in a garage, your brain would probably guess car battery or power tool. The raw data, the sensation, is identical, but your perception changes because of your top-down knowledge.
So we really do see what we expect to see.
To a very large and very efficient degree, our brains are prediction machines. It's faster to guess based on context than to rebuild the world from scratch every single second.
Okay, so before we dive into the biology of the eye, we have to talk about how we even measure any of this. How do you quantify a perception?
This is where we get into the field of psychophysics.
Psychophysics, it sounds like a mashup of psychology and physics.
That's literally what it is. And it was pioneered by a truly interesting character in the 19th century named Gustav Fechner.
Right, number 11 on our list.
Yep. He was a physicist and also a philosopher, and he had this really audacious goal. He wanted to measure, scientifically, the relationship between the physical world and our mental experience of it.
So not just that a light is on, but how bright it feels.
Precisely. He wanted to link the physical magnitude of a stimulus, like the actual weight of a rock in grams, to the psychological magnitude of the sensation, how heavy that rock feels to you.
Because those two things are not the same.
Rarely are they a one-to-one relationship. So Fechner and his successors developed methods to measure our limits. And the most basic limit they looked for was the absolute threshold.
This is like the hearing test at the doctor's office, right? Raise your hand when you hear the beep.
That's basically it. The formal definition of the absolute threshold is the minimum amount of stimulation needed for a person to detect its presence 50% of the time.
Why 50%? Why not 100?
Because biological systems are noisy and messy. You might think it's a hard line, at 10 decibels you hear nothing, at 11 you hear it perfectly.
It's not a switch.
It's not a switch, it's a gradient. If we actually graph this, we get what's called the psychometric function. It's a beautiful S-shaped curve. As the intensity of the stimulus gets stronger, the probability of you saying, yes, I see it, slowly goes up from 0 to 100%.
And that 50% mark is the sweet spot we call the threshold.
It's the agreed-upon scientific standard. Now, there are a few key methods for measuring this that are still used today.
Okay, let's run through them. This is how the actual science gets done.
Right. First up is the method of limits. It's pretty straightforward. I present tones to you in an ascending series, getting louder, until you say, yes, I hear it. Then I do a descending series, getting quieter, until you say, no, I don't hear it anymore.
And you just do that over and over.
Many times. And we take the average of all those crossover points, where you went from yes to no or no to yes. That average gives us a pretty good estimate of your threshold.
Simple enough. What's method 2?
The method of adjustment. This was the fastest, but it's also the least accurate. I just give you a dial that controls the brightness of a light, and I say, turn this until you can just barely see it.
So it puts the control in the subject's hands.
Which is fast, but it's also very subjective. Some people might be more cautious, others more liberal in their judgment.
Okay, so what's the gold standard?
The method of constant stimuli. This is the most accurate, but it takes a very long time. I pre-select 5 or 6 different intensities. Some I know you can't see, some you definitely can, and some in between.
And you just show them to me.
In a completely random order, hundreds of times. And for each one, you just say yes or no. Because it's random, you can't predict what's coming next, so it eliminates any bias from expectation. We can then plot that data and get a very precise psychometric function.
Got it. So that helps us find the absolute floor of our senses. But what about telling the difference between two things?
Now you're talking about the difference threshold, or the just noticeable difference. It's not about what you can detect, but what change you can detect.
So if I'm holding a weight, how much more weight do I need to add for me to notice it's gotten heavier?
Exactly that. And what a guy named Weber discovered, this is Weber's law, is that the difference threshold isn't a fixed number. It's a ratio.
What do you mean a ratio?
For weight, the ratio is about 0.02, or 2%. That means if you're holding 100 grams, you'll notice a difference when I add 2 grams. But if you're holding 1,000 grams, you won't notice that 2-gram difference. You need me to add 20 grams.
So the more intense the initial stimulus, the bigger the change has to be for you to notice it.
Precisely. For light intensity, the ratio is about 8%. For electric shock, it's only 1%. Our senses are tuned differently for different inputs.
And there's one more psychophysics concept here that's really interesting, the oblique effect. Item number 8 on our list.
Yes. The oblique effect is a perfect example of how our perception is shaped by the world we live in. It's a simple fact. Humans are much better, more sensitive at perceiving horizontal and vertical lines than slanted or oblique ones.
Why is that?
Well, think about the world you grew up in. Trees grow vertically. The horizon is horizontal. Buildings are made of verticals and horizontals.
Our world is built on a grid.
It is. And our brain has adapted to that.
Yeah.
We actually have more neurons in our visual cortex dedicated to processing vertical and horizontal orientations than any other angle. It's a case of biology mirroring the statistics of our environment.
That is wild. Our brain is literally optimized for our planet.
In so many ways. Okay, so that's the world of psychophysics, the math behind perception. Shall we leave the lab and get into the wetware?
Let's do it. Time for the anatomy lesson. We're going to do a full tour of the structure of the eye. I want to follow a single photon of light from the moment it leaves the sun to the moment it hits the back of your eyeball.
A great way to frame it. Okay, so light is a form of energy. It travels in waves, and it's part of the vast electromagnetic
And
spectrum,
we only see a tiny fraction of it.
in an infinitesimally small sliver. What we call visible light is just the waves with a wavelength between about 400 and 700 nanometers. Everything else, radio waves, microwaves, X-rays, is invisible to our eyes.
Okay, so a photon from that visible spectrum is heading towards my face. What's the very first thing it hits?
It hits the cornea. This is the transparent, dome-shaped window at the very front of your eye.
And this is more than just a protective shield, right?
Oh, much more. Most people think the lens does all the focusing, but the cornea is actually responsible for about 80% of the eye's focusing power. It does the initial coarse bending of the light rays, but it's fixed. It can't change its shape.
Okay, so light is bent by the cornea. Then it passes through the hole in the middle of my eye, the pupil.
Right, and the pupil isn't really a structure, it's just an aperture, a hole. It looks black because it's like looking into a dark room, the inside of your eye.
And the size of that hole is controlled by the colorful part, the iris.
Exactly. The iris is a muscle, so what gives your eyes their color. And it controls the size of the pupil in a process called the pupillary reflex.
If it's really bright outside, my pupil gets tiny.
The iris constricts it to limit the amount of light coming in, protecting the sensitive cells at the back of your eye. When it's dark, the iris dilates the pupil, opening it up wide to let in as much light as possible.
I've heard that a smaller pupil actually gives you a sharper image.
It does. It increases your depth of field. It's the same principle as the aperture setting on a camera. A smaller aperture or pupil means that more of the scene, from near to far, is in focus at the same time.
Okay, so the light has passed through the pupil, now it hits the lens.
Now it hits the lens. The lens is the fine-tuner. While the cornea did the heavy lifting, the lens can change its shape to adjust the focus for objects at different distances.
And how does it change shape? It's not a muscle itself, is it?
No, it's controlled by the ciliary muscle, which is attached to it by tiny fibers. When you want to look at something close up, like a book, the ciliary muscle tightens.
Which you'd think would pull the lens flat.
Counterintuitively, it actually allows the lens to relax and bulge out, becoming thicker and more curved. This increased curvature bends the light more sharply, which is what you need to focus on near objects. This entire process is called accommodation.
And this is the system that starts to fail as we get older.
It's one of the first things to go. As we age, the lens naturally hardens and becomes less flexible. So even when the ciliary muscle tightens, the lens can't bulge out as much as it used to.
Which means you can't focus on close-up things anymore.
Exactly. Your near point, the closest distance at which you can focus clearly, starts to move further and further away. You find yourself holding your phone at arm's length. That condition is called presbyopia, which literally means old eye.
No, that's different from just being nearsighted or farsighted, right? Let's clarify those terms. We have emmetropic, myopic, and hyperopic.
Right. An emmetropic eye is a perfect eye. The length of the eyeball is perfectly matched to the focusing power of the cornea and lens, so light focuses exactly on the retina.
So what's a myopic eye?
Myopic is the scientific term for nearsighted. In this case, the eyeball is typically a little too long. So the light from distant objects comes to a focus in front of the retina. By the time the light actually hits the retina, the image is blurry.
And hyperopic.
Hyperopic is farsighted. Here, the eyeball is a bit too short. So the focal point for near objects would actually be behind the retina. The lens has to accommodate constantly, even for distant objects, which can cause a lot of eye strain.
Okay, so our photon of light has been bent by the cornea, passed through the pupil, been fine-tuned by the lens, and now it's traveling through the main chamber of the eye.
Which is filled with a clear, jelly-like substance called the vitreous humor. Its main job is just to maintain the shape of the eyeball and keep everything in place.
And at the very end of that journey, it hits the screen, the retina.
The retina. This is where the magic really begins. It's a thin layer of tissue at the very back of the eye, and it's packed with the cells that will actually detect the light.
But the structure of it is bizarre, right? The notes say it's inside out.
It is so strange. You'd think the light-detecting cells would be at the front to catch the light first, but they're not. They're at the very, very back.
So the light has to pass through a bunch of other stuff first.
It has to pass through several layers of other neurons. It goes through the ganglion cells, the amacrine cells, the bipolar cells, and the horizontal cells before it finally reaches the actual photoreceptors, the rods and cones.
That seems like a terrible design, like putting the microphone behind the speaker.
It does seem that way, but evolution clearly made it work. And on this retinal screen, we have very distinct zones. There's a central area called the macula.
And in the middle of the macula.
In the very center of the macula is a tiny pit called the fovea, or the foveal pit.
This is the important part.
This is the most important part of your retina for detailed vision. The fovea is tiny, but is packed exclusively with cones. There are no rods here. This is your high-definition 4K color center. When you're reading these words, your eye is making tiny movements to place each word directly on your fovea.
So what about everything outside the fovea?
That's all considered the periphery, and the periphery is the opposite. It's dominated by rods. It's not great for seeing fine detail or color, but it is incredibly good at detecting motion and seeing in very low light.
The corner of your eye vision.
Exactly. It's your early warning system. Now, there is one spot on the retina that has no receptors at all. No rods, no cones.
The blind spot?
The blind spot. This is where all the axons from the ganglion cells bundle together to form the optic nerve, which is the massive cable that leaves the eye and goes to the brain.
There has to be an exit.
And at that exit point, there's just no room for photoreceptors. It's a literal hole in your vision.
So why don't I see a black hole floating in my field of view right now?
Top-down processing. We're back to that. Your brain is a master at filling in the gaps. It looks at the surrounding pattern and just paints it in. It makes a very good guess about what should be there, and you never notice the hole is gone.
That's amazing. Now let's talk about when this incredible hardware starts to break down. We mentioned two conditions earlier: macular degeneration and retinitis pigmentosa.
Two very different and devastating conditions. Macular degeneration primarily affects older adults, and as the name suggests, it attacks the macula.
So it attacks the center of your vision.
The fovea, exactly. You lose your high-definition central vision. You can't read. You can't recognize faces. But your peripheral vision, your rod-based vision, often remains intact. You can see the room, but not the person in front of you.
And retinitis pigmentosa.
That's a genetic disease that often works in the opposite way. It typically attacks the rods in the periphery first. So the first symptom is usually night blindness.
Because the rods are for night vision.
Correct. Then you start to lose your peripheral vision. It creates a tunnel vision effect that slowly closes in over years until only a tiny window of central foveal vision might be left.
Okay, let's zoom in even further. We've reached the photoreceptors themselves, the business end of the retina, the rods and the cones.
This is where light finally meets biology, and the numbers here are just staggering. In each eye, you have about 120 million rods.
120 million.
And only about 6 million cones. So you have 20 times more rods than cones.
Let's talk about the cones first, since they seem to be for our primary daytime vision.
They are. Cones give us our perception of color and our ability to see fine detail. And they come in 3 different flavors, which is topic 53 on our list.
The 3 types of cones.
They're defined by the wavelength of light they are most sensitive to. We have short wavelength cones, or S cones, which absorb light best at about 419 nanometers. We perceive this as blue.
Okay.
Then there are medium wavelength cones, or N cones, which peak around 532 nanometers. That's in the green part of the spectrum. And finally, long wavelength cones, or L cones, which peak at 558 nanometers in the yellow-red part of the spectrum. Your perception of all colors is just the combined activity of these 3 cone types.
And what about the rods? What's their specialty?
Rods are the masters of night vision. They are incredibly sensitive to light, much more so than cones, but they are completely colorblind. They only come in one type.
And they have a preferred wavelength, too.
They do. This is the basis of their absorption spectra. Rods absorb photons best at a wavelength of about 500 nanometers, which is kind of blue-green color. This is why, in very dim light, bluish objects can actually look brighter than reddish objects. Your rods are doing all the work, and they're biased towards blue.
Okay, this is it, the big moment. We're at topic 3, transduction. This is where the light officially becomes a biological signal. How does this happen?
This is visual transduction and is one of the most elegant processes in all of biology. It happens inside the outer segment of the rod cell.
What's in there?
The rod is packed with these little discs, and embedded in the membrane of those discs are millions and millions of molecules of a visual pigment called rhodopsin.
Rhodopsin, that's the key chemical.
That is the key. And rhodopsin itself is made of 2 parts. There's a large protein called opsin, and nestled inside it is a small, light-sensitive molecule called retinal.
So what are these 2 parts doing when it's dark?
In the dark, the retinal molecule is in a bent shape, and it's attached snugly to the opsin protein. It's just sitting there waiting.
And then the photon arrives.
And then the photon arrives. This is the crucial moment. When a single photon of light is absorbed by that retinal molecule, the energy causes the retinal to instantly straighten out. It changes its shape.
And that's it. That's the trigger.
That's the entire trigger. That tiny molecular shape change is called isomerization. That's the biological switch being flipped.
Wow.
And that single isomerization event sets off a massive chemical chain reaction, a cascade, that closes ion channels in the cell membrane and ultimately creates the electrical signal that the brain can understand.
And the sensitivity of this system is just insane, right?
It's operating at the absolute limit of physics. The research is clear. It takes only 1 photon to isomerize a single rhodopsin molecule.
1 photon.
And the minimum amount of rods needed for perception for your brain to register I saw a light is just 7. If 7 different rods anywhere in your retina each catch 1 photon at roughly the same time, you will see a flash of light.
That's almost unbelievable. But what happens to that retinal molecule after it straightens out?
Well, once it's straight, it doesn't fit inside the opsin protein anymore, so it breaks away. It detaches.
Okay.
When the retinal separates from the opsin, the rhodopsin molecule becomes lighter in color. This process is called pigment bleaching. And once it's bleached, it's used up. It can't absorb another photon. It's offline.
So how do we see for more than a fraction of a second? How does it reset?
This is where visual pigment regeneration comes in. A series of enzymes has to find that detached retinal, bend it back into its original shape, and reattach it to the opsin molecule. And this process takes time.
And this explains why it takes a while to adjust to the dark. This is the dark adaptation curve.
This is exactly what the dark adaptation curve shows. It's one of the most famous graphs in perception science. When you walk from a bright sunny day into a dark movie theater, you're functionally blind for a moment.
Because all your rhodopsin is bleached.
Every last molecule. So your visual system has to start regenerating it. The curve shows how your sensitivity to light increases over time in the dark.
Walk me through the shape of that curve. It's not a smooth line, is it?
No, it has 2 distinct stages or limbs. For the first 3 to 4 minutes, your cones are adapting. They regenerate their pigment relatively quickly. But cones aren't very sensitive to begin with, so your vision improves, but then it hits a plateau.
And then what happens?
Then, around the 7 to 10 minute mark, something critical happens. You hit the rod cone break.
The baton pass.
It's a perfect analogy. This is the point where the regenerating rods become more sensitive than the fully adapted cones. So the rods take over the job of seeing.
And the rods just keep getting better.
They keep getting better. The second stage of the curve, which is all rod-based, continues for another 20 to 30 minutes. Your sensitivity just keeps increasing and increasing until you reach your absolute threshold.
How do scientists prove this is about rods and cones? What are the dark adaptation methods?
A couple of clever ways. To measure just the cone adaptation, they can shine a tiny test light only on the fovea, because the fovea has no rods.
So you isolate them.
Exactly. And to measure just the rods, they can study people who are rod monochromats.
These are people with a rare genetic condition.
Right, item 46. Rod monochromats are born without any functioning cones. They are completely colorblind and extremely sensitive to bright light. But by testing their dark adaptation, we can see the pure rod curve without any interference from the cones. It's a perfect match for the second limb of the normal curve.
So we've done it. We've turned a photon into a chemical reaction involving retinal and opsin, and that has created an electrical signal. We've defined sensitivity as being the inverse of the threshold. Now we need to figure out what happens to that electrical signal.
Now we enter the nervous system. We are officially in section 4, neural processing. We have to talk about neurons.
The basic building block at the brain.
The fundamental unit of communication. You have the cell body, you have dendrites, which are like antennae that receive signals, and a long cable called an axon that transmits signals. But the currency here isn't chemical anymore, it's electricity.
Let's talk about potentials. The notes mention resting potential, graded potential, and action potential.
Okay. A neuron that isn't doing anything is at rest. But it's not idle. It's like a loaded battery. It's actively pumping ions across its membrane to maintain an electrical charge difference. It's more negative inside than outside. This difference is the resting potential, and it's typically about negative 70 millivolts.
So it's polarized.
It's polarized and ready to go. Now, when a signal comes in from another neuron, it can cause a small temporary change in that voltage. That's a graded potential. It might nudge it a little, but not much happens.
But if the signal is strong enough,
If the incoming excitatory signals are strong enough to push the voltage past a certain trigger point, about negative 55 millivolts, then all hell breaks loose. You get an action potential.
the spike, the neuron fires.
It fires. This is depolarization. Gates in the membrane called sodium channels fly open, and positively charged sodium ions rush into the cell. The voltage inside shoots up from negative to positive, up to about plus 40 millivolts in a thousandth of a second,
And that electrical wave travels down the axon.
like a lit fuse. And for that signal to travel quickly and efficiently, especially over long distances, the axon needs insulation.
Which is myelinization.
Yes. The axon is wrapped in a fatty sheath called myelin. It acts just like the plastic insulation on a copper wire, preventing the electrical signal from leaking out.
And when that insulation is damaged, it's catastrophic.
This is the cause of multiple sclerosis, item 65. The immune system attacks and destroys the myelin sheath. The signal degrades, it short circuits, and communication between neurons fails. In the optic nerve, this can cause vision loss or blindness.
So the action potential reaches the end of the axon. But neurons don't actually touch each other, do they? There's a gap.
A tiny, tiny gap called the synapse. And the electrical action potential cannot jump that gap. So the signal has to change forms again. This is where neurotransmission or synaptic transmission occurs.
It goes from electrical back to chemical.
For a brief moment, yes. The arrival of the action potential triggers the release of chemicals called neurotransmitters from the end of the axon. These chemicals float across the synapse and bind to receptors on the next neuron's dendrite.
And these chemicals carry different messages.
Broadly, two main types. You have excitatory neurotransmitters and inhibitory neurotransmitters.
Excitatory is the go signal.
Exactly. They cause a small depolarization in the next neuron, making it more likely to fire its own action potential. Inhibitory neurotransmitters are the stop signal. They do the opposite. They hyperpolarize the next neuron, making it less likely to fire.
So every neuron is constantly doing this map, summing up all the go and stop signals it's receiving.
All day, every day. It's not just a simple relay race. It's a massive ongoing computation. And a huge part of this computation, especially in the retina, is a concept called neural convergence.
Right. This seems critical. Neural convergence is about how many neurons feed into the next one in the chain.
It's a wiring principle, and it explains the fundamental trade-off in the retina between sensitivity and detail.
We have 126 million photoreceptors, rods and cones combined. But the optic nerve is only made of about 1 million ganglion cell axons. That's a huge data compression.
Massive bottleneck. And the way that compression happens is through retinal convergence, but the ratio is completely different for rods and cones.
Okay, let's get into the numbers. Item 81 on our list. For rods, it says the convergence ratio is about 120 to 1.
That's the average. 120 rod cells all connect to a single ganglion cell. This is a highly convergent circuit.
What's the advantage of wiring things that way?
Sensitivity. Extreme sensitivity. Think of it like 120 tiny streams all flowing into one river. A single drop of rain in one stream won't do much. But if a little bit of rain falls on all 120 streams, the river will rise.
So weak signals from many rods can add up to trigger the ganglion cell?
Exactly. The rods pool their resources. This is why you can see in such dim light.
Yeah.
But there's a huge downside. Detail. Or acuity. When that one ganglion cell fires, the brain gets a signal. But it has no way of knowing which of the 120 rods that feed into it actually saw the light. The location information is smeared out and fuzzy.
Okay, now let's look at the cones. The ratio is much lower, about 6 to 1 on average.
Much lower convergence. But in the fovea, the center of your vision, it gets even better. It's a 1-to-1 ratio.
One cone connects to one ganglion
A
cell.
private line of the brain. This is a simple circuit, or a linear one.
So what's the consequence of that wiring?
Well, the downside is low sensitivity. That one cone has to get hit by a lot of light all by itself to make its ganglion cell fire. There's no pooling of resources. This is why your fovea is useless in the dark.
But the upside must be incredible detail.
Perfect detail. If that one ganglion cell fires, the brain knows with pinpoint accuracy exactly where on the retina the light fell.